So, hello, thank you for joining. And could you start by introducing yourself?
Sure. So my name is Giovanni. I'm one of the creators and founders of RocketPy. I'm currently a mechanical engineer working part time in RocketPy as an open source developer. Mainly, I'm the lead of the public relations and outreach team. So I seek out university teams wanting to contribute to RocketPy and university competitions or startups, everyone that may be interested in RocketPy in one way or another.
Okay, what inspired the creation of RocketPy?
So RocketPy was born out of essentially my passion for rocketry and programming when I was starting university. So I joined university back in 2015, and I joined a rocketry team named Project Jupiter, and we started developing our own in-house simulation code, which I think is pretty natural for most university teams. Essentially, when we are in university, we have this desire of applying what we learn in class to what we are doing. And there we were essentially designing rockets from the ground up to participate in competitions such as the Spaceport America Cup. So we wanted to apply what we learned from dynamics and numerical methods, and we started creating the first line of codes of RocketPy. Back then, it didn't even have this name, but we chose to do it in Python. One of the main aspects that made us create our own code instead of using what was already available was especially how wind was modeled in the softwares that were already available. So we thought that uh, wind could really affect the trajectory of a rocket, especially during a recovery with a parachute, such as the main parachute or the drogue parachute. So wind could really move the rocket towards east, south, north, or whatever, depending on where the wind is pointing. And we really focused in the beginning on creating or integrating weather models that were more realistic than other softwares could essentially do already. So that was one of the main focuses in the start of RocketPy, which really inspired us to create our own code instead of using what was already available. And later on, still in 2016, if I'm not mistaken, we were participating in a competition, which was essentially the first rocketry competition in Brazil. The competition doesn't really exist anymore, but it was a very nice tournament that happened in a space launch center here in Brazil called CLBI. And the military staff at that Space Launch Center required us to perform detailed analysis of dispersion ellipses of where the rocket would land after launch. And doing that with the software already available was quite challenging for us. We needed to do many of the things manually. So that was also a big part of working on RocketPy and enhancing its features, tailoring it to support such features such as Monte-Carlo analysis and dispersion analysis. I guess that summarizes essentially the main things that inspired us to create RocketPy in the first place.
So, you would say that the major advantage of RocketPy over other simulation software is the ability to more accurately simulate wind?
That's definitely one of the main features of RocketPy, not simulating, but integrating atmospheric models such as wind forecasts or reanalysis, which are essentially historical data, or even soundings, which can be done with balloons, which go up in the atmosphere and collect wind data. It's much easier for us to integrate that data into RocketPy and then simulate the rocket trajectory with that, comparing with other softwares. In the beginning, I would say that was the main differential thing. Nowadays, we have a lot of new features which are already setting us apart from different software out there.
What would be the main functionalities of RocketPy?
The main functionalities, I guess, we need to just taking a step up and seeing RocketPy from above. It's important to understand that RocketPy was designed with the intent of serving the needs of university rocket teams, at least at first. Nowadays, we see the market changing, and we can talk about that later. But our main focus was serving university rocket teams, and we wanted to create something which was very flexible and modular, kind of a framework so that we could simulate rocket trajectories. Uh, and in that sense, we needed to have a language that most university teams could talk in a sense in terms of programming language. And Python was essentially, it's quite recent in terms of popularity. It's quite new when compared to other programming languages such as C or Java, but it was really gaining traction back then. And we opted to work with Python because most universities were teaching introduction to programming in Python. So we said, all right, let's create a library in Python so that teams can work with, because they're already going to learn that in university. And then we created this set of the Python library, which teams could use to simulate their own rocket. Now they can build a lot of things around it. So they can build optimization around it and machine learning around it, and test their own uh, avionics firmware with RocketPy. They can do a lot of things with RocketPy, wrapping it, since it's a Python library. So in terms of architecture, that really sets it apart. But in terms of specific features, besides the atmospheric conditions and models that I mentioned, most recently we implemented hybrid and liquid motor support, which is something which was lacking from other options available. So very few software can simulate accurate flights with hybrid and liquid motors, because most rockets, especially uh, before this decade, most rockets or high power rockets were built with solid motors. And now university teams are moving to hybrid motors and liquid motors. And these motors are quite different from solid motors because they have liquid parts, and liquid parts behave differently. Their center of mass changes different from a solid motor. Their inertia tensor changes differently. So we really made a quite hard effort to support this, because we saw that many teams were starting to build these motors. And we partnered with Space Enterprises at Berkeley, which is a university team from the University of Berkeley, so that we could understand how to model these motors better and implement them into RocketPy. So that's one of the main features nowadays as well. Another very important feature is integration with Matlab. Many students either know Python or are very familiar with Matlab. In engineering, Matlab is very common. So integration with Matlab is also a very important feature of RocketPy. And besides that, I already mentioned this, but the ability to have the code that runs in your rocket to trigger the parachutes during events. So during apogee, or when you're trying to trigger a parachute release at a certain altitude, all of these codes can be essentially simulated if they're working well, if they're detecting these events well, with RocketPy in a sort of software in the loop framework through parachute triggers. So that's also something that we are very proud of.
So, like, you can put the rocket software inside of RocketPy, and it would see if it would like open the parachute at the right time.
Exactly. So essentially, what happens is, imagine you have your rocket software that you essentially upload to your microcontroller on your rocket. What you can do, you have various options, but what you can do is you can make RocketPy communicate with it, so that during a RocketPy trajectory simulation, RocketPy sends, for example, pressure data to your code. Most parachute triggering codes use pressure data to determine if the rocket has reached apogee or a certain altitude. But RocketPy can send a lot of data. Pressure is just one of them. And we even emulate noise into this data, so it's more realistic of what the code would be receiving in a real flight. So RocketPy sends this pressure data to the software and waits for the software to say, all right, now it's time to trigger the parachute. And now when it says, all right, trigger the parachute, then RocketPy knows that it's changing from a flight phase where the rocket was being powered, ascending to a new phase where now the rocket will be deaccelerated by a parachute and probably descend under a parachute.
How do you ensure the accuracy of RocketPy's simulations?
Now, ensuring accuracy is a tricky part, especially in the beginning. We didn't have that kind of mindset because we were really eager to just implement new features. Most recently, I would say in the last 2 or 3 years, we started taking really good care of that. Uh, the way we do it is we separate, we do several different kinds of tests to ensure accuracy and reliability. So the most basic kind of tests that we do, and these tests are all automatic. We call them unit tests. It's a very common test in the programming world. Essentially, what they do is They take each function inside RocketPy and give the expected input and check for the expected output. So they make sure that each function, each unit of RocketPy is working properly. And then we have more complicated tests, which are called integration tests, which make sure the RocketPy as a whole is working well, not having any bugs or not causing any errors during execution when we are combining all of these functions together. And then finally, the most interesting kind of tests is acceptance tests, where we feed RocketPy with real world rocket data and flight data, and we compare this RocketPy simulations with the flight data to make sure that the predictions of apogee or maximum velocity or impact point, impact velocity, all of these different parameters match or have a good agreement between simulation and real flight data. And we have a couple of this acceptance tests already integrated into RocketPy from launches from teams which partnered with RocketPy to supply this data. Now, Project Jupiter, which was where RocketPy was born, is one of the rockets is from them. We also have data from a rocket from EPFL, which is an European university, and we also have one from an American university, which is Notre Dame Rocketry team. So we have these three main rockets that were launched, and we have real flight data that every time we make a change to the code in RocketPy, these simulations are checked to see if they're producing the expected results comparing to real flight data. Now, our participation in EuRoC has supplied us with a lot more data. We have a lot more rockets and a lot more flight data, and we're starting to process and analyze all of this data that we have so that we can integrate them into this testing framework that RocketPy uses to make sure it's reliable and accurate. And in the future, we expect to have much more than just these three rockets with rocket data from EuRoC.
What role did RocketPy play in the EuRoC team's preparation?
This year was the first year that EuRoC really advised teams to use RocketPy. So in the rules, teams were allowed to submit their rocketry simulations using other software, even in-house code. But they were also advised to submit RocketPy simulations. And since it was the first year for that, some teams had never really used RocketPy before. It was quite challenging for them to learn RocketPy quickly and be able to submit this. So we have a channel in Discord where teams ask questions and we help them out. But I would say that from all the feedback that we got during this year's European Rocketry Challenge, most teams use RocketPy, especially in the final stages of their rocketry development, to input their final model into RocketPy and check that it was producing the expected apogee and other outputs from the simulation. And then later on, they would use this data during EuRoC itself to submit this data to the staff, and that was part of their grading, and was also a very important part of the launch campaign, where RocketPy simulation data was used to determine if a rocket was landing at a safe spot, if it could be landed, if it could be launched, if the launch was safe, and a series of different analyses that were done by both the team and the staff at EuRoC. So RocketPy really did change a bit of things of how teams worked this year to submit their simulations. I'm sure that some teams had it easier than others, but in the end, most teams or all teams did a fantastic job with their simulations and really gave us very well-made and well-tailored simulations that produce good results.
Could you provide an example of a situation where RocketPy significantly changed an outcome at EuRoC?
So I don't want to mention specific team names here for respecting their privacy, but we had a couple of cases in EuRoC this year where we had to RocketPy data essentially caused the team to not be able to launch at first. When we are analyzing a launch at EuRoC, we get the simulation from the team and we modify it a little bit to consider different scenarios. So essentially, consider different things that can go wrong during a rocket launch. So after you launch your rocket, one of the main things that can go wrong and have a high probability of going wrong is the triggering of the parachutes. So sometimes no parachutes are triggered and you get a ballistic flight where the rocket lands at very high, maybe supersonic speeds. That's very dangerous. That's pretty much like a missile. Other times, essentially the main parachute can open at apogee, and that is quite challenging because that means that the main parachute can either open at a high velocity depending on the horizontal velocity of the rocket, but most importantly, the main parachute really makes the rocket descend slowly, and if there's a lot of wind, that means that the rocket gets dragged away very far away from the launch area. And that can be a problem because the rocket may end up landing on a nearby town or a nearby city, which can be dangerous. So this year, Rocket at EuRoC, we had this problem where more than one Rocketry team uh, had a very far away landing in case the main parachute were to open at apogee. And we showed this data to EuRoC staff and the military team that were organizing safety regulations. They said that the team could not launch under those conditions because the rocket would essentially have a high probability of falling in a nearby town. So the team did a lot of hard work, and we helped them as we could through the simulations to change how the rocket would fly to make sure that that wasn't a problem. And after they fixed that problem, essentially, and the new RocketPy simulations showed that it would land safely at all possible scenarios, then the team got the go ahead to launch. So essentially, RocketPy simulations can cause a little bit of problems for the teams if their landing points or if there's something that isn't quite right in terms of the regulations. But that's very important because we are one of the many steps to ensure the safety of a launch operation during the European Rocketry Challenge. And we were very happy that we were able to contribute to that safety and that the teams were able to modify the rockets inside to make sure that everything was going to happen as safely as possible.
What features do you want to add to RocketPy in the future?
There are a lot of features coming. We're working on these features constantly. RocketPy is an open source project, so anyone can work on them, but we have a whole team of developers, which are volunteers working on these features. I would say that the most anticipated feature right now is the new controller class that we're adding to RocketPy. Essentially, it will allow for a better integrated simulation of active controllers in the rocket. Nowadays, a lot of rockets have active stabilization for control. Some rockets are even starting to do thrust vector control. But many rockets have, for example, air brakers, which are also actively controlled and serve to guarantee that the rocket will achieve the desired apogee that the team set by slowing down the rocket if it's going too fast. But it needs to control how much it's slowing down the rocket to make sure that the apogee is correct. So we see a lot of teams implementing active control in their rockets, even for recovery using parafoils. So we have worked quite hard. And actually, during EuRoC this year, we already had a prototype code of this implementation, and now we're refining it, working alongside the teams so that we can release it probably still by the end of this year if everything goes all right. We'll have a new version of RocketPy which can simulate controllers much better than it could before in a much more integrated environment with allowing teams to use this set of new features to model their rocket properly. Now, controllers is something that's really going to differentiate us from other rocketry trajectory simulations out there because I would say none of them support controllers right now. So that's a really important thing. We see that teams are always adding new things for their rockets, new technology, and it's hard for software to keep track of that and to stay on top of teams. So RocketPy, the entire team is working really hard with the teams to make sure that we can simulate what they have on their rockets so that they can make sure that their simulations are as accurate as possible. And besides controllers, I would like to add another feature which is important is a more universal aerodynamic model. So RocketPy already allows importing outside aerodynamic data, but that's kind of tricky to do right now. So we're going to generalize it a lot and be able to import aerodynamic data as a whole, every single aerodynamic coefficient from CFD analysis or wind tunnel analysis or things like DATCOM or different aerodynamic analysis software. So that's also something very important that is coming soon. Some specific features dedicated to run Montecarlo and dispersion analysis Right now, we use a wrapper around RocketPy to do that, and it works very well, but it definitely requires more advanced skills. And we're bringing that into the main set of features of RocketPy so that it's easier for teams to implement and do, and also works faster than what we have today. So that's the main features that are expected soon, and we have a whole roadmap that can be seen through our GitHub page. We have a set of issues and a set of milestones that we want to accomplish in the future, and anyone interested can visit our GitHub page for the RocketPy repository and see everything that we're working on currently.
What advice would you give to rocketry teams that are starting to use RocketPy?
So for new teams starting to use RocketPy, I would advise them to start with our example simulation. We have a getting started notebook where you can pretty much run a couple of code snippets that generate an entire rocket simulation, an entire rocket trajectory simulation. You get all the inputs and all the outputs as expected. I would say start from there, learn from there, and then start modifying that simulation, start modifying that example for your rocket, and then test step by step to make sure that all the changes you're making make sense, don't break the code that you're running, and give you the expected results. Now, it's really important to consider when using any simulation software, in fact, the accuracy of the results that you're getting really depends on the accuracy of the inputs that you're giving the software. You gotta strive to have really accurate and really precise data in terms of the mass of the rocket, the thrust curve of the motor, aerodynamic coefficients. So the input data that you give is really crucial to get good results. So don't just focus on the simulation itself. Spend a lot of time making sure that your inputs are correct, that your inputs are accurate, and that your inputs are up to date as most as can be. Because we know that designing rockets is a very dynamic environment and things are changing all the time. So sometimes the simulation team responsible to run the trajectory simulation ends up using out of date data, and that can be really bad because you get bad results that don't reflect the real results that your rocket will deploy. So it's really important to make sure your data is correct.
How does RocketPy integrate with other tools used in rocketry?
RocketPy supports importing thrust curves in the most common formats out there. One of them is the .eng, ENG format for thrust curves. You can get those thrust curves from motor suppliers and even from websites such as thrustcurve.org. That's one of the basic features. We also have, quite separate from RocketPy, but also developed by the RocketPy team of developers, a Open Rocket serializer. The name is quite confusing, but essentially it's a way to get an Open Rocket file, a simulation file, and convert it into RocketPy so that you can simulate your rocket also using RocketPy and compare the results between Open Rocket and RocketPy. That's also an easier step for new teams. Most teams nowadays have used Open Rocket for quite a while now. And when they're transitioning to use RocketPy as well for more detailed and accurate analysis, it's a nice thing to have their simulations being converted into a RocketPy format so that they can understand this translation process and see how things work. So that's also how RocketPy integrates with other technologies that are used out there. We see from the RocketPy community, there's a bigger effort recently to make things work together more seamlessly. So RocketPy, OpenRocket and Razor are also working together to make file conversion between different softwares easier. And it's very nice to see all of this softwares being able to talk to each other and convert between their formats easily so that the user can have the option to simulate their rockets in very different softwares and see if their results are as expected, if everything seems okay before they launch their rocket, so that they can be as secure as possible that they have a good rocket to launch.
What was the most rewarding experience you had for EuRoC?
The most rewarding experience at EuRoC this year was definitely interacting with the teams and working together with them to make sure that their simulations were running smoothly and all right. It was very nice seeing how much effort the teams were putting into their simulations, and they really wanted to do a good job and have an accurate simulation as a result. as I mentioned before, some teams had it easier than others, so some teams did have a little bit of difficulty getting to the desired result, but we helped them as much as we could, and it was very nice interacting with them. It really showed that everyone was working together towards the same goal. Even though we were part of the staff of the European Rocketry Challenge this year, it was very nice seeing that cooperation between staff and the teams was very smoothly, and most of the rockets were able to launch successfully. So that was very rewarding for us. I'm gonna be honest and say that since it was the first year that every team needed to submit or were advised to submit RocketPy simulations, we were expecting that some teams weren't going to be very happy with this because they were already used with their old ways, with their old types of simulations. But all teams were very open to it and wanted to do a good job. So that was very nice working with them as a whole. It's important to know that RocketPy is completely open source, worked on by volunteers. So we have a whole team of developers working in RocketPy. Very recently, we actually had a new incorporated new members into our team. So we've grown from about 12 to about 20 or more than 20 team members working in RocketPy. And it's very nice to see the diversity of people we have. So we have people from Asia, we have people from Europe, from the United States, from South America, from Canada. We have people from all over the world right now working in RocketPy. We have very experienced people working on their PhD. We have engineers working in the field. We have members of university teams, senior members, junior members of university teams. So we have a very nice diversity of people currently working in RocketPy. Our main goal is to have an open source solution for everyone that is interested in high power rocketry to use and to be able to contribute to. And we want the solution to be as up to date as possible and follow the progress that the university teams are having. Recently, the university teams and even startups in the field of aerospace are having huge progress on new technologies. And we noticed that the options available out there, be closed source or open source options, weren't being able to keep up with all of these new innovations. So it really struggle and strive in RocketPy to make sure that we are keeping track of these innovations and trying to integrate them into our simulations as fast as possible so that teams can have simulations as tools to improve their projects instead of simulations holding them back. And it's very, very nice to be a part of this team. And there's a lot of very talented people working on this and giving a part of their time for free as volunteers to develop this and have the best simulation solution out there for everyone to use. Now, there are a lot of other solutions out there that work very well. And even inside RocketPy, we use them to improve ourselves and to compare that everything is working right. So RocketPy will never eliminate them. That's not our goal. We have a different target. We want to make something modular, flexible, really create a framework for more experienced users to use. We're very happy to be part of this rocketry community, and in the stages that it is right now, it's very hot and growing very quickly. So it's really nice to be a part of all of this. The thing about RocketPy is since it's a Python library, it's very easy to create custom code to communicate between different solutions and RocketPy. So usually with a few lines of code, you can integrate an outside solution with RocketPy. Thank you very much, Etto, for this interview. Here at RocketPy, we really appreciate the work that you're doing in terms of communication and promotion of everything that is happening in the rocketry society nowadays. We're very excited about everything you do, and we follow your work very closely. It was an honor for us to be interviewed by you, and hopefully we can have further interviews in the future as things move along and new things come up. Thank you very much.
Thank you.